Welcome back to mathkernel and to the finale of the scalar product chapter. One honest word first. Integrals, Fourier series, and Legendre polynomials come up less often than the rest of this chapter. This is the conceptual capstone, the payoff that a scalar product needs no arrows and no Rn at all. What always carries over is the abstract reasoning, checking the axioms, and that orthogonal vectors are independent. So watch this one to understand the idea deeply. 12 problems. Pause whenever you'd like. Problem 1. The integral of a product turns functions into a Euclidean space. Verify the three axioms and pin down exactly where continuity does its quiet, essential work. Pause and try. Bilinearity and symmetry are immediate. The integral is linear in each factor, and f times g equals g times f inside it. So the first two axioms cost nothing. Positivity. A function with itself is the integral of f squared. The integrand is a square, never negative, so the integral is at least 0. So far, so easy. The subtle axiom is the second half of positive definiteness. If that integral is 0, must f be the 0 function? For a general function, no, but here's where continuity enters. Suppose f is non-zero somewhere. Say f of x naught isn't 0. Because f is continuous, f squared stays above half of f of x naught squared on a whole little interval around x naught. Integrating a strictly positive bump over an interval of positive width gives a strictly positive area, so the integral can't be 0. Contradiction. So for continuous functions, the integral vanishes only for the 0 function, and it's a genuine scalar product. Drop continuity, allow a function that's non-zero at a single point, and the integral is still 0 there, so it's only a semi-norm. Continuity is the exact hypothesis that rescues positive definiteness. Problem 2. A function has a length, the square root of its product with itself. Compute it for x squared. Pause and try. The norm squared is the function with itself. Here the integral of x squared, which is x to the fourth, from -1 to 1. Integrate x to the fifth over 5, evaluated at the endpoints. A fifth minus a negative fifth, 2/5. So the length of x squared is the square root of 2/5, which tidies to root 10 over 5. The green area under x to the fourth is that norm squared, made visible. 2 more you'll reuse constantly. The constant function 1 has length root 2, the whole width of the interval, and x itself has length root 2/3. Every polynomial now has an honest length. Problem 3. Two functions are perpendicular when their integral product is 0, and on a symmetric interval, parity often decides it instantly. Pause and try. Take x and x squared. Their product is x cubed, and orthogonality asks whether its integral over -1 to 1 is 0. X cubed is an odd function, and any odd function integrated over a symmetric interval gives 0. The negative half exactly cancels the positive half, as the shaded areas show. So x and x squared are orthogonal. But be careful, orthogonality isn't automatic. 1 and x squared. Their product is x squared, an even function, and its integral is 2/3, not 0. So 1 and x squared are not perpendicular. The rule to internalize. On a symmetric interval, an even function and an odd function are always orthogonal, and two evens or two odds generally are not. That single parity check saves enormous amounts of integration, and it's exactly what makes Gram-Schmidt on polynomials so clean, as we'll see. Problem 4. Functions have angles between them, too. The same cosine formula, now with integrals. Pause and try. Same recipe as for vectors. The the scalar product over the two lengths. The product of 1 and x plus 1 is the integral of x plus 1, which is 2. The x part integrates to 0, the 1 part to 2. The norms. 1 has length root 2, and x plus 1, squared and integrated, gives 8/3, expand to x squared plus 2x plus 1, whose integral is 2/3 plus 0 plus 2. Now the cosine. 2 over root 2 times the root of 8/3. The denominator is 4 over root 3, so the whole thing is 2 root 3 over 4, which is root 3 over 2. And root 3 over 2 is the cosine of 30 degrees. So these two functions sit at a 30-degree angle. Length and angle, the entire geometry, carry over from arrows to functions unchanged. Only the scalar product is now an integral. Problem 5. The trigonometric functions are pairwise orthogonal, the fact that makes Fourier series work. Prove one such case with a product to sum identity. Pause and try. The trick is to turn the product into a sum. The product to sum identity writes cosine x times cosine 2x as 1/2 of cosine x plus cosine 3x. Now integrate each piece over a full period from minus pi to pi. A cosine of any non-zero integer frequency integrates to 0 over a full period, equal positive and negative humps, canceling, as the shaded areas show. So both integrals vanish, and the whole thing is 0. Cosine x and cosine 2x are orthogonal. The same product to sum move handles every pair. Different frequencies are always perpendicular. And a companion fact for normalizing. Cosine x with itself, the integral of cosine squared, is pi. Using cosine squared equals 1/2 of 1 plus cosine 2x. That pi is the normalization constant we need next. Problem 6. The trig functions are orthogonal. Now make them orthonormal by dividing out their lengths. Pause and find the constants. First, the lengths. The constant 1, squared and integrated over minus pi to pi, is just the width, 2 pi. Every cosine kx and sine kx has norm squared pi, from the same cosine squared computation as before. So normalize by dividing each by its length. 1 over root 2 pi for the constant, cosine kx over root pi, and sine kx over root pi. The cross terms between a cosine and a sine are 0 for free. Their product is odd, so it integrates to 0 over the symmetric interval. Put it together, and you have an orthonormal system, an infinite orthonormal basis of the function space. This is the trigonometric ONS, and Fourier series are simply coordinates with respect to it. Problem 7. The centerpiece. A function's Fourier coefficients are its coordinates in the trig system, each one a single integral. Compute them for x squared. Pause and try. First, symmetry does half the work. X squared is even, so its product with any sign is odd, and every sign coefficient integrates to 0. The series is pure cosine. The constant term a0 is the average, 1 over pi times the integral of x squared, which is 2 pi cubed over 3, giving 2 pi squared over 3. Its half, pi squared over 3, is the mean value the series settles around. The cosine coefficients need integration by parts, twice. The sign boundary terms die at plus and minus pi, and what remains is 4 times minus 1 to the k over k squared. So a1 is minus 4, a2 is 1, a3 is minus 4/9, decaying like 1 over k squared. A symbol x squared is pi squared over 3, plus the sum of 4 minus 1 to the k over k squared, times cosine kx. Watch the partial sums on the left. S1 already captures the bowl shape, and S3 hugs the parabola tightly. A few cosines rebuild a parabola. Problem 8. a genuinely delightful payoff. The Fourier coefficients of x squared secretly encode two famous infinite sums. Extract them. Pause and try. First, just evaluate the Fourier series at x equals pi. There, cosine k pi is minus 1 to the k, so it multiplies the existing minus 1 to the k to give plus 1. And x squared at pi is pi squared. So pi squared equals pi squared over 3, plus 4 times the sum of 1 over k squared. Solve for the sum. Pi squared minus pi squared over 3 is 2/3 pi squared, divided by 4. The sum of 1 over k squared is pi squared over 6. That's the Basel problem, dropping straight out of a Fourier series. For the fourth powers, use parseval, the function space Pythagoras. The average of f squared equals the sum of the squared coefficients. The left side, 1 over pi times the integral of x to the fourth, is 2 pi to the fourth over 5. The right side is a0 squared over 2. That's 2 pi to the fourth over 9, plus 16 times the sum of 1 over k to the fourth. Solve, and the sum of 1 over k to the fourth is pi to the fourth over 90. Two celebrated sums, both delivered by the geometry of a single parabola. This is the deepest reason the abstract theory is worth knowing, even if it isn't the everyday workhorse. Problem 9. Projection onto a subspace, now in function space. The closest trig combination to a given function is its truncated Fourier series. Find it for f of x equals x. Pause and try. The best approximation in a subspace is the orthogonal projection onto it, and in the trig system, that projection is just the truncated Fourier series, keeping only the constant, cosine x, and sine x terms. Now f of x equals x is odd, so its products with the constant and with cosine x are odd. Those coefficients vanish. Only the sine coefficient can survive. b1, 1 over pi times the integral of x sine x. Integrate by parts. The integral of x sine x from minus pi to pi comes out to 2 pi, so b1 is 2. So the best trig approximation of the line f of x equals x on this interval is simply 2 sine x, the green curve, which is exactly the degree 1 Fourier partial sum. Least squares in function space is Fourier truncation. The two ideas are one. Problem 10. Gram-Schmidt doesn't care whether the vectors are arrows or polynomials. Orthonormalize 1, x squared under the integral product. You'll rediscover the Legendre polynomials. Pause and try. Start with the constant 1. Its norm squared is 2, so e1 is 1 over root 2, a flat, normalized constant. Next, x. It's already orthogonal to the constant, because x times 1 is odd and integrates to 0, the parity trick from earlier. So no subtraction needed, just normalize. Its norm squared is 2/3, so e2 is root 3/2 times x. Now x squared. It's even, so it is not orthogonal to the constant, and we must subtract its shadow. The scalar product of x squared with 1 is 2/3 over the norm squared of 1, which is 2, so subtract 1/3. That gives x squared minus 1/3. Note it's automatically orthogonal to x already, again by parity. Find its length. The integral of x squared minus 1/3, all squared, works out to 8 over 45. Normalize, and e3 is the root of 45 over 8 times x squared minus 1/3, which tidies to 1/2 root 5/2 times 3x squared minus 1. Those are exactly the first three Legendre polynomials, the constant, the line, and the parabola 3x squared minus 1. Gram-Schmidt on powers of x generates them, 1 degree at a time. Problem 11. Pull a scalar product back through a linear map, and you get a new form. When is it still a scalar product? The single condition is injectivity. Prove it. and test a map. Pause and try. The pullback pairs v and w by first sending them through psi, then taking the original product. Bilinearity and symmetry are inherited directly. Psi is linear, and the original product already has them. So the first two axioms are automatic, injective or not. Everything hinges on positive definiteness. V with itself in the pullback is the norm squared of psi v, which is 0 exactly when psi v is the 0 vector. So the form is positive definite, 0 only for v equal to 0, precisely when the only vector psi sends to 0 is 0 itself. That is exactly the statement that psi is injective. Injective, and it's a scalar product, non-injective, and some non-zero vector has 0 length, breaking the axiom. Test the map sending x, y to x, x plus y. It's injective, its determinant is 1. The pulled-back form, v with itself is x squared plus y squared, which expands to 2x squared plus 2xy plus y squared, with gram matrix 2, 1, 1, 1. Check that matrix is positive definite by Hurwitz. The top left entry 2 is positive, and the determinant, 2 minus 1, is 1, positive. So it's a genuine scalar product, as guaranteed, because psi was injective. Cite injectivity only at the positive definiteness step. That's the whole subtlety. Problem 12, the finale, and the one abstract idea from this whole chapter that genuinely shows up on exams, even on spaces that aren't functions at all. 2 short proofs. Pause and try. Part A is the continuity lemma from problem 1, standing on its own, the archetypal function space proof. If f is non-zero at some point, continuity keeps f squared above half that value across a little interval of width 2 delta, forcing the integral strictly positive. So a zero integral, for a continuous function, means f is identically 0. Learn this argument as a template. Part B is the idea that travels everywhere. Claim, any set of non-zero, pairwise orthogonal vectors is linearly independent. Suppose a combination sums to 0. Hit the whole equation with the scalar product against one vector, ej. Every cross term vanishes by orthogonality, leaving cj times the norm of ej squared. Since ej is non-zero, its norm squared is positive, forcing cj to be 0, and this holds for every j. The vectors are independent. Apply it to the signs of distinct frequencies, which we showed are orthogonal, infinitely many of them, all independent. And here's why this matters beyond functions. This exact argument, orthogonal implies independent, is the one that keeps coming back, whether the vectors are functions, matrices, or infinite sequences. The integral setting is where the idea is prettiest, but the idea itself is the transferable one. That's the note to end the chapter on. And that completes the scalar product chapter. We saw the same 3 axioms play out on arrows, on matrices, on complex vectors, and finally on functions, where they hand you Fourier series, Legendre polynomials, and famous infinite sums as a bonus. Keep the honest perspective. This last topic is the beautiful capstone more than an everyday workhorse, and the single idea that carries furthest is the abstract one. Verify the axioms, and orthogonal means independent. 5 theory videos, 5 exercise sets, 1 whole idea of geometry. If this series helped, give it a like and tell me in the comments what to cover next. Support the channel on Patreon, link below. Thanks for watching. I'll see you in the next chapter.